Okay, so we're going to do the same problem we did before, but we're going to do it differently. Okay, so we have this vector field. We want to find the line integral of this vector field. C is the boundary of this downward-facing paraboloid oriented upward. Okay, now C is a key thing. So we want to find the line integral around C. Now, C is the boundary. Yes, it is the boundary of that surface right there. But what other surface is it the boundary of? C is also the boundary of the surface x squared plus y squared is equal to 2, and z is equal to 0. In other words, it's the boundary. In other words, it's the boundary of the disk of radius 2 in the xz plane. Okay, so by Stoke's theorem, the integral that we care about is the integral over this surface of the curl of f. This surface integral of a vector field. Okay, so we'll go ahead and compute curl of f again. I, j, k. This is 2y minus, backwards, x, y, z, 2y minus 2x, 0. Okay, the first component is 0. The second component is also 0. And the third component is minus 4. Okay, now remember that by definition, the line integral of a vector field is equal to the surface integral of a vector field is a surface integral of this scalar field. Okay, so now what is the normal vector? Well, the normal vector is just going to be 0, 0, 1. In other words, it's just going to be k. Because this is the surface, the surface is a disk of radius 2 in the xy plane. Now, the surface that we start off with, the paraboloid surface that we start off with is important here because it has an outward pointing orientation, okay? This induces a counterclockwise orientation on the curve, and so to apply Stoke's theorem, we need to get a consistent orientation on this disk, and that means it's going to be k. The only two choices are plus and minus k. But the orientation on the paraboloid gives us an orientation on the curve. The orientation on the curve gives us an orientation on the surface, and that's going to be k. So n is equal to k. So this is the surface integral over the surface S minus 4 ds. Okay, now using what I talked about in the video, so you don't have to do this. So let me just say right away, this is equal to minus 4 times the area of S, which is equal to 4 pi. Okay, but if you want to do this a little more explicitly, okay, this is a surface integral of minus 4 over a surface ds. Remember from one of my previous videos, the one where I sort of give a tip about computing surface integrals where the surface is in a coordinate plane. This is the integral, just the normal integral over the parameter domain S, which is the circle of radius 2, centered at the origin, minus 4 dA. And now this is going to be the integral theta equals 0. If I switch to polar coordinates, theta equals 0 to 2 pi, r equals 0 to 2, minus 4r dr d theta, and this is just equal to minus 4 times 4 pi. Okay, this right here, this part right here, come on. Well, it's not undoing. Okay, this part right here, that part right there I just did because I wanted to illustrate that tip on computing surface integrals from one of my previous videos. But really, this is how you should do it here. You're doing the surface integral of minus 4. That's equal to minus 4 times the area of the surface. The surface is a disk of radius 2 centered at the origin, so you get minus 16 pi. Which is what we got in the previous example. Okay, so this one we were kind of sneaky because we wanted to compute Stoke's theorem. We wanted to use Stoke's theorem, but we didn't use the surface that they gave us. We picked another surface that happened to have the same boundary. And this is a very important thing to be able to do in Stoke's theorem.